So with that introduction to the scheduling basics, we are now ready to dive into the discussion of some of the popular CPU scheduling algorithms. When we discuss various CPU scheduling algorithms, you will note that each scheduling algorithm is essentially a set of rules that help us select or decide an order in which a given set of processes need to execute. So that is essentially what each CPU scheduling algorithm is. Now, as you will see, different scheduling algorithms optimize different scheduling criteria. Recall that we just now talked about scheduling criteria on one of the previous slides. In this unit, we'll discuss both the non-preemptive as well as preemptive scheduling algorithms. Under the non-preemptive scheduling, we'll talk about first come first served, shortest job first, and non-preemptive priority scheduling. For the preemptive category, we'll talk about shortest remaining time first, Srtf for short, preemptive priority, and round robin scheduling algorithms. Here are various goals that different CPU scheduling algorithms are trying to achieve. So for instance, the CPU scheduling algorithms try to be fair to different processes and to different users, so that different user processes can get their fair share of time to execute on the CPU. The scheduling algorithms also try to be efficient. Efficiency means multiple things here. So first, trying to keep the CPU as busy as possible, doing useful work. Useful work here means executing the user processes. So essentially what that means is the CPU scheduling algorithms need to be able to quickly decide which user process should go next, so that the CPU is spending more time or most of its time executing the user processes as opposed to executing the CPU scheduling code itself. The schedulers also try to maximize the throughput so that we can get as many processes completed as quickly as possible. In general, they try to minimize the response time so that the users do not have to wait too long before they can start receiving responses from their system, from their processes, especially in interactive systems. The scheduling algorithms also try to be predictable. So by predictability here we mean if you run the same process multiple times, in general you should see similar turnaround times and similar response times. So the variance between these turnaround times and response times should not be large across multiple runs in the same system. That is predictability. These scheduling algorithms also try to in general minimize overheads. This also helps them be efficient. They try to maximize the resource use, which means trying to keep the devices, both the IO devices as well as the CPU, as busy as possible. And finally, in general, they try to avoid starvation. Essentially, no process should have to wait indefinitely long for its turn to execute on the CPU. They also enforce priorities. So high priority processes should get to execute first before the low priority processes get to execute. And finally, these scheduling algorithms also ensure that the system performance degrades gracefully when needed. So what that means is, as the system becomes more and more heavily loaded, the performance of the system should deteriorate gradually and not abruptly. Now note that these are some high level goals. A given specific scheduling algorithm may not be able to achieve all of them because some of them actually conflict with each other. So for instance, if a priority based scheduling algorithm is strictly enforcing priorities, and let's say there are a lot of high priority processes in the system, in that case the lower priority processes may begin to starve. So that's just one example of how some of these goals are conflicting. Alright, so let's dive into the discussion of actual CPU scheduling algorithms now. The simplest CPU scheduling algorithm that we'll talk about is the first come first serve scheduling. As the name implies, in the FCFS or first come first serve scheduling algorithm, the processes are picked for execution in the order of their arrival in the ready queue. The processes that request the CPU first, they are allocated the CPU first. The implementation of FCFS scheduling is pretty straightforward. The implementation essentially needs a first in first out queue. So let's assume this is the state of processes in the system. Process P2 arrives first and therefore it is at the head of the queue, followed by process P1 and followed by process P3. So this is our ready queue in first FCFS scheduling. So the way this will work is, let's say a new process P4 now enters the system. So the PCB or the process control block of this new process would be linked to the tail of this queue. And when the CPU is free, it would be allocated to the process that is at the head of this first come first served queue. Let's walk through this example to better understand the FCFS scheduling. Let's assume we have these three processes P1, P2 and P3 entering our ready queue. Let's assume that P1 requires 24 milliseconds to execute, P2 and P3 they both require 3 milliseconds to execute, and this is the order in which they entered the ready queue, right? So basically P1 entered first, followed by P2, followed by P3. This bar chart over here, this illustrates the schedule, the CPU schedule that would be generated by the FCFS algorithm for these processes in this example. In operating systems, this bar chart is actually known as a Gantt chart. So remember this term, Gantt chart. So P1 came in first. According to the FCFS scheduling algorithm, we will allow this P1 to execute first on the CPU. So let's assume that the execution starts at time 0. Because P1 requires 24 milliseconds to run, P1 would finish at 0 plus 24, basically 24 milliseconds. When P1 finishes, now we need to figure out which process should go next. So note that in FCFS will schedule processes in their arrival order, right? So next P2 had arrived. P2 arrived second, followed by P3. So we'll now pick P2 for execution on the CPU. So P2 will start at time 24, and because P2 requires 3 milliseconds, it would run until 24 plus 3, 27 milliseconds or 27 time units. And finally, when this P2 terminates at 27 time units, we'll let the last process P3 execute, and P3 will finish at 20 because it starts at 27 and requires 3 milliseconds. It will finish as 27 plus 3, 30 milliseconds. So this is how the schedule for this FCFS algorithm is computed. Now let's evaluate this schedule using the average waiting time for each of these processes. So note that all of these processes P1, P2 and P3, we are assuming that they all entered the system simultaneously here at time 0. So the start time for each of these processes is 0. Now P1 was scheduled immediately after entry at time 0. So P1 did not have to wait at all, right? So the wait time for P1 was 0. Now P1 finished at time 24. And after that P2 was scheduled, but P2 was waiting. It had arrived at time 0, but it got to run after P1 finished at time 24, right? So the wait time for P2 was 24 minus 0, which is 24 milliseconds. Similarly, P3, it entered the system at time 0, but it started execution here at time 27 after P2 ended, right? So the wait time for P3 is 27 minus 0, which is again 27 units. So the average waiting time for all the three processes is P1 waited 0 milliseconds, P2 waited 24 milliseconds, and P3 waited 27 milliseconds. So the average is 0 plus 24 plus 27 divided by 3, which is basically 51 divided by 3, which is 17 milliseconds. The solution is also summarized over here. Alright, so let's redo the previous example, but this time we'll change the arrival order. So all three processes P1, P2 and P3, they still enter the system at time 0, but they are admitted in a different order. So this time we'll assume that first process P2 was admitted, followed by process P3 and followed by process P1. So this is their arrival order now. Everything else is still the same, right? So P1 still requires 24 milliseconds to execute, P2 requires 3 milliseconds and P3 also requires 3 milliseconds to execute on the CPU. So let's see how this change in the arrival order affects the CPU schedule and the overall waiting time of these processes. So again, let's construct the Gantt chart. In this case, because P2 arrived first, the FCFS scheduling algorithm will first schedule this process P2 on the CPU. So P2 would start executing at time 0 immediately after entering the system, and it requires 3 milliseconds. So it will finish here at time 0 plus 3. Once P2 finishes, the CPU would be free again. So now we will choose process P3 to execute on the CPU because P3 entered the system second. So P3 starts at time 3 and it also requires 3 milliseconds. So it would finish at 3 plus 3, 6 milliseconds. And finally, when P3 finishes here at time 6, at this time the last process P1 would get to go and enter the CPU. It will start executing on the CPU and it will finish at 6 plus, it requires 24 milliseconds. So 6 plus 24, 30 milliseconds. So this is the schedule. Now let's see what are the individual waiting times in this case for each of these processes. So let's start with process P1 here, right? So process P1, note that it entered the system at time 0 because all three processes entered at time 0, but it began execution on the CPU at time 6, right? This is where process P1 started executing. This is at time 6. So process P1 had to wait 6 minus 0 for 6 milliseconds. For process P2, note that P2 got to run on the CPU first, right? So it entered the system at time 0 and it started execution at 0, so it had to wait for 0 milliseconds. And finally P3, note that P3 starts execution at time 3 over here after P2 finishes, right? So but it entered the system at time 0, so its wait time is 3 minus 0, 3 milliseconds. So in this case the average wait time for the three processes would be 6 plus 0 plus 3 divided by 3, which is basically 9 divided by 3 milliseconds. Recall, in the previous scenario or in the previous example, the wait time for the same processes, the same three processes, was for 17 milliseconds, but now that has gone down significantly to just 3 milliseconds simply because of this change in the arrival order. The solution to the second scenario is also illustrated here. With that background, let's quickly think about some of the advantages and disadvantages of Fcfs scheduling algorithm. Note that the first come first serve scheduling schedules every process for execution in their arrival order, and therefore all the processes will get a turn to execute. There is no scope of starvation in Fcfs scheduling. However, you should note that here we are assuming that all the processes have finite length of CPU burst. So for example, sometimes as a counter example, maybe an erroneous process has a never ending while loop, something like this. So such a process can execute forever on a CPU in Fcfs scheduling. Because Fcfs is a non-preemptive scheduling algorithm, the processes, once they start executing on the CPU, they can only voluntarily give up control of the CPU. The operating system cannot snatch away the CPU from the executing process, and therefore such erroneous or malicious process in Fcfs scheduling can hog the CPU forever. So I'm assuming that this kind of worst case scenario doesn't happen. There is going to be no starvation in Fcfs scheduling. So that's the first advantage. The second advantage is Fcfs scheduling is very simple to implement. You just need a queue. You just need to maintain a queue of ready processes and keep scheduling them in their order of arrival. Nothing more sophisticated is needed. On the other hand, here are some disadvantages. We have already seen in the previous two examples that we solved, the average waiting time under the Fcfs scheduling policy is greatly dependent on the order in which processes arrive. Usually the average waiting time for all the processes in the system under this Fcfs scheduling policy is not minimal. We have seen that a CPU bound process can hog the CPU for a long time, and all the other processes will have to wait behind it. The operating system cannot force any process out of the CPU because Fcfs is a non-preemptive scheduling algorithm. So we have seen that the Fcfs is not very predictable, mainly because the waiting times vary largely depending on how the processes arrive, the arrival order of the processes. And we have also seen that the CPU bound processes can hog the CPU in Fcfs scheduling. Another related disadvantage here is if there is, let's say, one CPU bound process which takes a long time to execute on the CPU, and many IO bound processes that are interactive and they have short CPU bursts, or you may have a scenario where you have few CPU bound processes and a large number of IO bound processes. Either way, you'll see a convoy effect in the system. Here you will see several short processes will wait behind one long process for their turn to execute on the CPU. This has multiple negative effects on the system. So first of all, it increases the response time for so many interactive processes. Second, it also reduces the utilization of the IO subsystem as well as that of the CPU subsystem. Here is another CPU scheduling algorithm, the shortest job first algorithm. The way this scheduling works is, this algorithm for each process estimates the length of its next CPU burst. When the CPU is available, it is assigned to the process that has the smallest next CPU burst or the shortest next CPU burst. In case multiple processes have the same next CPU bursts, then Fcfs scheduling is used to break the tie. So out of the processes that are in tie, the one that arrived first would be allowed to go first. Note that Sjf for short or shortage of first is also a non-preemptive scheduling algorithm. Once the CPU is given to a process, it will only be voluntarily released by the CPU when the CPU burst completes. Let's try to understand the workings of shortage of first or the Sjf algorithm better with the help of this example. For simplicity, in this example, we are going to assume that every process has just one CPU burst. There are 4 processes, P1, P2, P3 and P4, and their CPU burst times are as given in the table here. So this is the burst time. P1 has a burst time of 7 milliseconds, P2 has 4 milliseconds, P3 has 1 milliseconds, and P4 requires 3 milliseconds of CPU burst time. As a change, note that not every process here is arriving at time 0. The arrival times are indicated in the second column here. So P1 arrives at time 0, but P2 arrives at 2 milliseconds, P3 arrives at 4 milliseconds, and P4 arrives at 5 milliseconds. So given this information, let us try to complete the Gantt chart here for this process, for this Sjf scheduling algorithm corresponding to the given set of processes. So here at time 0, only process P1 would be present in the system. So there is no choice because there is only one process. This process has to be scheduled. So P1 gets to execute starting time 0, and it requires its burst time is 7 milliseconds. So it will finish here at time 7. So P1 executes from time 0 to 7 milliseconds. In the meantime, note that P2 will arrive at time 2 milliseconds. So here at 2 milliseconds P2 arrives, and P3 will arrive at time 4 milliseconds. So P4 arrives here at 4. And I'm sorry, P3 arrives at time 4 and P4 arrives at time 5. So P4 arrives here. So at time 7, P1 has finished. Now the CPU is free, so we have to pick one of these P2, P3 and P4 as the next process to execute. So for the shortage of first, we'll look at their burst times. Note that, and we'll pick the one that has the shortest CPU burst. So note that P3 has a CPU burst of 1 milliseconds as compared to 3 milliseconds of P4 and 4 milliseconds of P2. So P3 has the shortest CPU burst, therefore P3 gets to execute next. So we'll give the CPU to P3 and it will take 1 millisecond to execute. So it will start at time 7 and it will finish here at time 8. So here P3 finishes. So now P3 is done too. Next, we need to pick either P2 or P4, which are the remaining processes to schedule on the CPU. So P2 has a burst time of 4 milliseconds and P4 has a burst time of 3 milliseconds. So the shortage of first would pick P4 as the next candidate. So P4 will start executing here at time 8 and it has a burst time of 3. So it finishes at 8 plus 3, 11 milliseconds. So P4 executes next and finishes here. And finally, after P4 has finished, P2 will get to execute next, and P2 requires 4 milliseconds, so it will start at 11 and will finish here at time 15. Let us complete this table over here using the information in this Gantt chart. Let's first work on this termination time column. So note that P1 finished here at time 7, right? So the termination time for P1 is 7. P2, note that it finished here at time 15. So termination time is 15. P3, it finished here at time 8. So the termination time of P3 is 8, and P4 similarly finished here at time 11. So that goes here. Next is the turnaround time. Recall, the turnaround time is basically the time that elapses from the beginning of the process to its end. Essentially in this table, the turnaround time would be the termination time minus the arrival time. Therefore, the turnaround time for P1 is 7 minus 0. So that would be 7 minus 0, which is 7 itself. For process P2, it would be 15 minus 2. So 15 minus 2 is 13 milliseconds. For process P3, it would be 8 minus 4. So the 8 minus 4 is 4 milliseconds. And for process P4, it would be 11 minus 5. Right? So 11 minus 5 is 6 milliseconds. And finally, we need to compute the waiting time. Recall, the waiting time is the time that a process spends waiting for its turn to execute on the CPU in the ready queue. Now, in this case, the waiting time would simply be turnaround time minus the burst time. Because recall, in our examples, the processes either execute on the CPU or they are waiting for their turn to execute in the ready queue. So the burst time indicates the time that a process executes on the CPU. The turnaround time is the total of the time the process is spent executing on the CPU and the time it's spent in the ready queue waiting for its turn to execute. Therefore, the waiting time is turnaround time minus the burst time. So let's do this. Process P1, the waiting time would be the turnaround time, which is 7, minus the burst time, which is also 7, right? So 7 minus 7 is 0. For process P2, it would be 13 minus 4. So 13 is the turnaround time and 4 is the burst time. So this would be 9 milliseconds. For process P3, it would be 4 minus 1. So 4 minus 1 is 3 milliseconds. And similarly for process P4, it would be 6 minus 3, which is basically again 3 milliseconds. So based on all of this information, let's now compute the average waiting time for all the processes. So that would basically be simply an average of all these waiting times in the last column. So that would be 0 plus 9 plus 3 plus 3 divided by 4, because there are 4 processes, which is basically 15 divided by 4, which is essentially 3.75. The answers are also summarized over here. So with that background, let's think about the advantages and disadvantages of this scheduling algorithm. The main advantage of the shortest job first algorithm is that it is provably optimal in the sense that it gives minimum average waiting time for a given set of processes. No non-preemptive algorithm can do better than this in terms of average waiting time. So why is that? As you have seen, the shortest job first algorithm schedules the processes that have shorter CPU bursts ahead of the ones that have longer CPU bursts. It turns out that moving a short process before a long one decreases the waiting time of the short process more than it increases the waiting time of the long process. And that is why the average waiting time overall decreases. Also, because the Sjf algorithm prioritizes processes that have short CPU bursts, it ends up favoring IO bound processes. Now these IO bound processes, they typically are also interactive processes. Most of the interactive processes are IO bound processes, and therefore the Sjf algorithm decreases the response time for such IO bound and interactive processes. So that's another advantage of this scheduling algorithm. But there are also some drawbacks. One of the important drawbacks here is starvation is possible in this scheduling, right? So note that in a heavily loaded system, let's say where there are a lot of interactive jobs with short CPU bursts that keep coming up. So in such a system, the large CPU bound processes, the processes that have long CPU bursts, they may never get to execute on the CPU because there would always be at least one short IO bound process ahead of them that will get prioritized. So that's one disadvantage. The starvation of long CPU burst processes is possible here. Another disadvantage is once a process that has a large CPU burst gets access to the CPU, it can hog the CPU for a long time because this is a non-preemptive scheduling algorithm. A long CPU burst process cannot be forced out of the CPU, and this could worsen or deteriorate the response time for the other IO bound processes or the interactive processes waiting behind this long CPU bound process. Finally, I should also mention that the real difficulty with the implementation of shortest job first algorithm is accurately predicting or knowing the length of the next CPU request or the next CPU burst. In practice, knowing the exact length of the CPU burst of a process in the short term is extremely difficult. It's hard to accurately predict the length of the next CPU burst of most processes in the short term. Next is non-preemptive priority scheduling algorithm. In this algorithm, a priority number, which is essentially an integer, is associated with each process. The integer represents the priority of the process. Anytime the CPU is available, it is allocated to the process that has the highest priority among all the processes in the ready queue. If multiple processes have the same priority, then FCFS, the first come first served algorithm, is used to break the tie. Note that the shortest job first algorithm that we talked about earlier is a special case of this priority scheduling algorithm. In the Sjf algorithm, essentially the priority of every process is determined based on the CPU burst length of the process. So the processes that have a shorter CPU burst, they get a higher priority. Now, having said that, different operating systems have a different convention to interpret the priority number associated with each process. In this course, unless stated otherwise, we'll always assume that a smaller number indicates a higher priority. So for instance, let's say these are some processes in our system, and here are the corresponding priorities. So P1 has a priority of 1, P2 has a priority of 0, and P3 has a priority of 2. So according to our convention, P2, which has the smallest priority number, has the highest priority, followed by P1, which has a priority of 1, followed by P3. So P3 has the smallest priority here because it has the highest priority number amongst all the three processes in this example. Next, how do we determine the priorities of the processes? Well, the priorities can be defined either internally by the operating system, or they can be specified externally by some administrator. Various different factors are used typically to determine the priority of the processes. Some of them are summarized here. So in general, the processes that are interactive in nature, or so these processes typically also tend to have shorter CPU burst because these are IO bound processes. They tend to get higher priority. Similarly, if we have important processes, well, let's say they are doing some critical task for the system, or maybe there are processes from important users that are high paying customers in the system, their processes can also be associated with higher priorities. If we have real time processes, so real time processes typically have a deadline associated with them. They need to be completed before the deadline. If not, the results could be catastrophic. So such processes also get higher priority in the systems. Likewise, system processes that are doing some critical tasks, they can also be associated with higher priorities. As opposed to this, processes that have long CPU burst times, or maybe belonging to the users, less paying customers, other less important system processes, or batch processes, or processes that tend to run in the background, all of these processes can have a lower priority in the system. So here are some advantages and disadvantages of non-preemptive priority scheduling. The main advantage of this approach is that the critical processes or important processes which we can associate with higher priority, such processes will typically see lower wait times and good response times with priority scheduling, because they would be scheduled on the CPU at higher priority. They will get preference over other processes. So that's a good thing. However, on the downside, processes that have low priority in the system, they can actually starve. So in a heavily loaded system where high priority processes keep coming in steadily, it is possible that certain lower priority processes almost never get to execute on the CPU, or they may have to wait indefinitely for their turn to execute on the CPU. So that's one drawback. Another drawback here is, since this is a non-preemptive scheduling algorithm, once, let's say, a low priority process that has a long CPU burst gets access to the CPU, it can hog the CPU for as long as it wants. It cannot be preempted out of the system or out of the CPU. All other higher priority processes or more important processes will have to wait for this lower priority CPU bound process to finish. We have seen that both the shortest job first as well as the priority scheduling algorithm suffer from the problem of starvation. Like we have seen, the shortest job first is just a special case of the priority scheduling algorithm, where the priority is estimated based on the CPU burst time. Short processes with short CPU burst, they get a higher priority in the shortest job first algorithm. And because of their scheduling mechanisms, both of these algorithms can leave some low priority processes waiting indefinitely. This could especially be a case in a heavily loaded computer system where a steady stream of higher priority processes keep coming in, and they will continue to prevent a low priority process from executing on the CPU. Well, so how can we fix this problem of starvation? A popular technique for addressing starvation is aging. In this technique, essentially, we gradually increase the priority of a low priority process in the system as it waits in the system for its turn to execute on the CPU. Let's assume that the range of priority values in our operating system range from 127, which is the lowest end, to 0, which is the highest end. Let's assume an extremely low priority process starts with the lowest possible priority of 127 in our system. Now, if we have aging implemented, what we can do is, for periodically, let's say every second that this process waits in the system for its turn to execute on the CPU, we can decrement the priority value, or in other words, we can increment the priority of this process by 1, right? So every second we'll go on increasing the priority of this process by 1. So this will change from 127 to 126 to 125 to 124 every second, right? And so on. Eventually the priority of this process would reach 0, at which point it will execute on the CPU. So this is how aging works, by periodically increasing the priority of low priority processes or waiting processes so that eventually they get to execute on the CPU. Now, another simple solution to address the starvation would be to define a maximum wait time in the system. So for example, let's say we define this maximum wait time to be 3 minutes. So once a process has crossed this maximum wait time without getting any chance to execute on the CPU, its priority can be set to the highest, and at that point it will immediately get to execute on the CPU. Recall earlier we talked about the shortest job first algorithm, which was a non-preemptive scheduling policy. However, the shortest job first algorithm could either be preemptive or non-preemptive. The preemptive version of shortest job first is known as shortest remaining time first algorithm. The way this works is, in the shortest remaining time first algorithm, when a new process enters the ready queue and another process is already executing on the CPU, we'll check both their CPU bursts. If the CPU burst of the newly arrived process is shorter than the remaining time of the currently executing process, then in this Srtf, or shortest remaining time first algorithm, the newly arrived process will preempt the currently executing process and the new process will start executing on the CPU. Let's try to understand the workings of Srtf algorithm better with the help of this example. Let's assume we have these 4 processes, P1, P2, P3 and P4 in our system, and they arrive in the indicated order. Process P1 arrives at time 0, P2 arrives at time 2, P3 arrives at time 4 and P4 arrives at time 5. P1 has a CPU burst of 7 milliseconds, P2 has a burst of 4 milliseconds, P3 has 1 millisecond and P4 has a burst of 3 milliseconds. Let's compute this Gantt chart over here to figure out how the Srtf scheduling algorithm would schedule these processes. So P1 arrives here at time 0, P2 arrives here at time 2, P3 arrives at time 4 over here and P4 arrives at time 5 over here. Let's also note down their burst times. So P1 has a CPU burst of 7 as indicated here, P2 has a burst of 4, P3 has a CPU burst of 1 and P4 has a CPU burst of 3. At time 0, there is only one process in the system, P1, so it gets to execute on the system. Now the next process arrives here at time 2. So by this time P1 has already executed for 2 milliseconds on the CPU. So let's compute its remaining CPU burst, right? So P1 has executed for 2 milliseconds. So the remaining CPU burst would be 7 minus 2, 5. And P2 has a CPU burst of 4. Therefore, the CPU burst here of the newly coming process is shorter than the remaining time of the currently executing process. And so P2 would preempt process P1. So now P2 would start executing on the system, and this will continue until this time 4, at which point P4 enters the system. So again, we need to run the shortest remaining time first algorithm to figure out which process should continue execution on the CPU. So note that at this time we have process P1 which has a remaining CPU burst of 5. We have process P2 and P2 had an original CPU burst of 4, but at this point it has already executed for 2 seconds, 2 milliseconds, right? So it now requires 4 minus 2, 2 more milliseconds. And P3, which is the newest process, it only requires 1 millisecond, right? So P3 has a burst time of 1. So note that out of these three processes that are present in the system, P3 has the shortest CPU burst, and therefore P3 will preempt P2, the currently executing process, and it will start executing on the CPU. So P3 has only 1 millisecond, so it will finish at time 5, and at time 5 P4 will also enter the system. So here at time 5, basically P3 has finished. We have process P1 which requires 5 milliseconds. We have process P2 which requires 2 more milliseconds, and P4 which has just now entered, it has a CPU burst of 3 milliseconds. So out of these three processes, P2 has the shortest remaining time, and therefore P2 would get to execute next based on the Srtf algorithm. So P2 gets to execute, and it finishes its execution at time 7, 5 plus 2. So it exits here at time 7. After P2 finishes, we now have processes P1 and P4. So P1 requires 5 more milliseconds on the microprocessor, as opposed to this P4 requires just 3. So P4 gets to execute next, which has the shortest burst here. So P4 executes for 7 plus 3 up to time 10 over here, and when P4 finishes, P1 is the last process remaining, so P1 will get to execute for 5 more milliseconds, and it will finish here at time 15. So based on this Gantt chart over here, let's fill up this table. So the first column here is the termination time. Note that, so for P1, process P1 finishes here at time 15. So the termination time is 15. For process P2, note that it was scheduled here and here, but it finally finished here at time 7. So the termination time is 7. Likewise for process P3, it was scheduled here and it finished at time 5. And finally for process P4, it was scheduled here and it finished here at time 10. Recall, the turnaround time is basically the termination time minus the arrival time. So for process P1, turnaround time would be 15 minus 0. So 15 minus 0 is 15. Similarly for process P2, the turnaround time would be termination time 7 minus the arrival time 2, which is 5. For P3, it would be termination time 5 minus the arrival time 4, which is 1. And for P4, it would be the termination time 10 minus the arrival time 5. So that is 10 minus 5 is 5. Finally, the waiting time. Recall, the waiting time is turnaround time minus the burst time. So for process P1 over here, the waiting time would be turnaround time 15 minus the burst time 7. So 15 minus 7 is 8. Similarly for P2, it would be turnaround time 5 minus the burst time 4, which is 1. For P3, it would be 1 minus the burst time 1, which is 0. And finally for P4, it would be the turnaround time 5 minus the burst time 3. So 5 minus 3 is 2. So based on this waiting time column, let's compute the average waiting time. That for these four processes, it would be 8 plus 1 plus 0 plus 2 divided by 4, which is basically 2.75. Let's think about some of the advantages and disadvantages of using the Srtf algorithm. The primary advantage of using Srtf is that this algorithm results in the minimum average waiting time for a given set of processes. No other scheduling algorithm can do any better in terms of the overall average waiting time. Also, because the shortest remaining time first algorithm always schedules the processes that have the shortest remaining CPU burst, it tends to favor the IO bound processes, which typically have short CPU bursts, and these also tend to be mostly the interactive user processes. So it's a good thing that the Srtf scheduling decreases the response time for such processes. Having said that, just like the shortest job first algorithm and the priority scheduling algorithms, in the Srtf scheduling, it is possible that the CPU bound processes that have long CPU bursts, they can starve. In a heavily loaded system where a stream of short CPU burst processes keep coming in, it is possible that a CPU bound process with a long CPU burst will almost never get to execute on the CPU, or maybe it will have to wait indefinitely to complete execution. Now once again, like we have talked earlier, we can use aging to prevent starvation with Srtf scheduling as well. Alright, so let's solve this class problem, which is asking us to create a Gantt chart for the given set of processes corresponding to Fcfs, Sjf and Srtf scheduling algorithms. So we have these four processes P1, P2, P3 and P4, and they arrive in the indicated order. So P1 arrives first at time 0, followed by P2 at time 2, followed by P3 at time 3, and finally P4 at time 5. Their burst times are P1 has 4 milliseconds, let's say P2 has 3 milliseconds, P3 has 5 milliseconds, and P4 requires 1 millisecond on the CPU. So let's start with the Fcfs algorithm. This is the most straightforward scheduling algorithm. Essentially the processes would be scheduled in the order they have arrived, right? So since they arrive in the order listed here, P1 arrives first, followed by P2, followed by P3, followed by P4. This is how they would be scheduled. So first P1 would be scheduled to execute on the CPU, and P1 has a CPU burst of 4, so it will start from time 0 and will end at time 4 over here. After P1, P2 would go next. P2 has a burst time of 3, so P2 executes on the CPU starting from 4 until time 4 plus 3, which is 7, right? So this is it, the P2 ends here at time 7. After this, P3 would be scheduled, which has burst time of 5, so it will start, P3 will start here at time 7 and it will end at 7 plus 5, this time 12 over here. So 7 plus 5 time 12. P3 ends over here. And finally P4 will be scheduled on the processor on the CPU, and P4 just requires 1 time unit, so it will start at 12 and it will finish at 12 plus 1 time 13. Next is the shortest job first algorithm. Let's mark the arrival of these processes in the Gantt chart. So P1 arrives here at time 0, followed by P2 arriving at time 2. So let's mark P2 here. P3 arrives at time 3, and finally P4 arrives at time 5. So P4 arrives here. Let's further note down their burst times. So P1 has a burst time of 4. So let's note that down here, 4. P2 has a burst time of 3. P3 has a burst time of 5. And finally P4 has a burst time of 1. Recall, the shortest job first algorithm schedules the process that has the shortest CPU burst on the CPU. But at time 0, there is only one process in the system, which is P1, and therefore P1 gets to execute. And recall that shortest job first is a non-preemptive scheduling algorithm, and therefore once the process P1 is scheduled, it will be allowed to complete its execution. So P1 requires 4 time units, so it will start at time 0 and will finish at time 4. At time 4 here, P1 has finished, and now we have two other processes P2 and P3 that have arrived in the meantime. So we have to choose one of these two. So note that P2 requires just 3 milliseconds as opposed to P3. So P2 is the shorter job, so P2 gets to execute next. So it will start at time 4 and will continue execution for 3 milliseconds. So it will finish at 4 plus 3, 7 milliseconds over here. So after P3 finishes, after P2 finishes, we now have processes P3 and P4 in the system. So P2 has finished. P3 has a CPU burst of 5 milliseconds and P4 has a CPU burst of 1 millisecond. So P4 is the shorter process, so P4 gets to execute next, and it just requires 1 millisecond. So it starts at time 7 and it will finish here at time 8. And after this, the only remaining process is P3. So P3 gets to execute for 5 milliseconds, which is its burst time. So it starts at time 8 and it finishes at 8 plus 5, 13 milliseconds. Finally, we have the shortest remaining time first algorithm. Once again, let's mark the arrival of the process and their CPU burst sizes here. At time 0, there is only one process in the system, which is process P1, and therefore P1 gets to execute on the CPU. So P1 begins execution, and at time 2, P2 arrives. So by this time, P1 has already completed 2 milliseconds of execution, and its original burst time was 4, but now at time 2, P1's remaining execution time is 4 minus 2, only 2 milliseconds. Now when P2 arrives at time 2, it has a CPU burst time of 3. So because the remaining time, execution time of P1 is shorter as compared to P2's, P1 continues execution. So P1 is not preempted, P2 is queued in the ready queue. Now at time 3 again, when process P3 arrives, P3 we will again have to evaluate whether the CPU burst of the executing process is shorter or longer than the newly incoming process. So P3 requires 5 milliseconds, and at this point at time 3, P1 has already executed for 3 milliseconds, so its remaining CPU burst is just 1 millisecond, and therefore P3 is also queued in the ready queue. P1 will not be preempted, so P1 will continue execution and will finish at here at time 4, which was its original burst time, 4 milliseconds. So P1 exits the system. Now at time 4 we have two processes, we have P2 and P3 in the system. So out of these two, the shortest remaining time first will pick the one that has shorter CPU burst, which is basically process P2, because it has just a CPU burst of 3 as opposed to 5 of process P3. So P2 gets to execute next on the CPU. However, at time 5 P4 comes in. So at this time at time 5 we have to reevaluate which process should be allowed to continue next on the CPU. So at this time P2 has already executed for 1 time unit and its original CPU burst is 3, so the remaining time is 3 minus 1, 2 milliseconds, and for P4 its CPU burst is 1 millisecond. Therefore P4 will preempt P2 and P4 would be allowed to execute, so it will start at 5 and it will finish at time 6. At this time P4 has completed, and now there are two processes, P2 and P3, remaining in the system. So recall that P2 requires 2 more milliseconds. This is the remaining CPU time. It has already executed for 1, and P3 it has a CPU burst of 5. So P2 is the shorter process, so P2 would be allowed to execute next and complete its remaining 2 milliseconds on the CPU. So it starts at time 6 and it will finish here at 6 plus 2, 8 milliseconds, and after this when the P2 has terminated, and now P3 is the only remaining process in the system, so it will be scheduled. It will start at time 8 and it will run for its 5 milliseconds, so it will terminate at 8 plus 5, 13 milliseconds over here. Just as we have a preemptive as well as a non-preemptive version of the shortest job first algorithm, we can also have a preemptive version of the priority scheduling. Recall, in the non-preemptive priority scheduling, every process is assigned a priority value, an integer which indicates its priority. Whenever the CPU is free, we select the process that has the highest priority for executing on the CPU next. The ties are broken between processes of equal priority by using FCFS, first come first serve. The preemptive priority scheduling would also do the same. In addition to that, the only difference here in the preemptive priority scheduling as compared to the non-preemptive version is that here, when a new process arrives in the ready queue, we'll compare the priority of this incoming process with the priority of the process which is currently executing on the CPU. If the new process has a higher priority as compared to the currently executing process, then the executing process will be preempted and the new incoming process will get to execute on the CPU. Let's walk through this example to better understand the workings of preemptive priority scheduling. So once again, we have these four processes, P1, P2, P3, and P4. Their arrival times and burst times are listed in the second and third columns respectively of this table, and their priorities are indicated here in the fourth column. So P1 has priority 3, P2 has 2, P3 has a priority of 4, and P4 has a priority number of 1. Recall that a smaller priority number indicates a higher priority as a convention for us. So let's complete this Gantt chart. Let us first mark the arrivals of each of these four processes on the time axis here. So P1 arrives here at time 0, followed by P2 at time 2, followed by P3 at time 4, and P4 at time 5. Let's also note down their priority numbers here. So P1 has a priority of 3, P2 has a priority of 2, P3 has a priority of 4, and P4 has a priority of 1. Alright, so let's start with time 0. At time 0, there is only one process in the system, P1, and therefore it gets to execute on the CPU. So P1 starts executing, and it executes until this point at time 2 in the system. At time 2, process P2 comes in, and P2 has a priority of 2, and P1 had a priority number of 3. So recall, P2 it has a smaller priority number, so P2 has a higher priority as compared to P1, and therefore P2 will preempt process P1, and P2 would get to execute on the CPU. So let's make a note that P1 has already executed for 2 time units, 2 milliseconds, and it has a burst time of 7, so its remaining time for P1 is 7 minus 2, 5 milliseconds. P2 executes until time 4 over here. P2 has a CPU burst of 4. Now at time 4, P3 comes in. Now note that P3 has a priority value of 4 and P2 has a priority of 2. So a smaller priority number is a higher priority. So P2 has a higher priority as compared to P3. So nothing to worry. P3 cannot preempt P2. So we continue. At time 5 over here, P4 also comes in. P4 has a priority number of 1. And note that P2 had a priority of 2. So P4 has a higher priority as compared to P2. So note that so far P2 has executed for 3 milliseconds from time 2 to 5, and P2 has a CPU burst of 4, right? So its remaining burst time is 4 minus 3, 1 millisecond. So at this time, at time 5, P4 preempts P2 and P4 gets to execute next. P4 has a CPU burst of 3, so it will execute until 5 plus 3, 8 milliseconds over here, and it terminates here at time 8. When P4 finishes, P1, P2 and P3 are remaining in the system. Now this is priority scheduling algorithm, so we will execute the highest priority process next. So among P1, P2 and P3, P2 has the highest priority, so P2 gets to execute next. Note that P2 had already executed for 3 milliseconds earlier, so it only has a remaining CPU time of 1 millisecond. So it will start at time 8 and it will finish at time 9. So after P2 terminates, we are remaining with P1 and P3. So among P1 and P3, note that P1 has a priority of 3 and P3 of 4. So P1 has a higher priority. So P1 goes next. P1 has a remaining CPU burst of 5 milliseconds. So it starts at time 9 and it will finish at 9 plus 5, 14 here. So P1 finishes here. After P1 exits, P3 is the only remaining process in the system, and P3 has a CPU burst time of 1 millisecond. So P3 starts at time 14 and it finishes at 14 plus 1 time 15. So based on this Gantt chart, let's complete the table over here. So for the termination time, note that P1 it first executed here, but then it finishes eventually at time 14. So the termination time for P1 is 14. Similarly, P2 it executed here and here, but it finished finally here at time 9. So that's the termination time. P3 got to execute just at the end, so and it finished at time 15. And finally P4 it executed over here and it finished at time 8. Let's work on the turnaround time. Recall again that turnaround time is basically termination time minus the arrival time. So for process P1, termination time is 14 and the arrival time is 0. So the turnaround time is 14 minus 0, 14 milliseconds. For process P2, it would be 9 minus the arrival time 2, which is 7. For process P3, the termination time is 15 and the arrival time is 4. So it's 15 minus 4, 11. And finally for process P4, the termination time is 8 and the arrival time is 5. So the turnaround time is 8 minus 5, 3. Finally, recall that the waiting time is basically turnaround time minus the burst time. So let's work on this. For process P1, the turnaround time is 14 and the burst time is 7. So waiting time would be 14 minus 7, 7 milliseconds. For process P2, turnaround time was 7 and the burst time was 4. So the waiting time would be 7 minus 4, 3. For P3, it would be 11 minus the burst time 1, which is 10. And finally for P4, it would be turnaround time 3 minus the burst time 3, which is 0 is the waiting time. So based on these values in the last column over here, let's compute the average waiting time for these 4 processes, which would be 7 plus 3 plus 10 plus 0 divided by 4, which is equal to, so this is 10 plus 10, 20 divided by 4, which is basically 5 milliseconds. Note that the advantages and disadvantages of preemptive priority scheduling are fairly similar to the ones we saw in non-preemptive priority scheduling. The main advantage here is again that with preemptive priority scheduling, the higher priority processes will see low wait times. And once again, the primary disadvantage is starvation. In a heavily loaded system where high priority processes keep coming in steadily, the processes that have low priority may have to wait indefinitely for their turn to execute on the CPU. Once again, we can use aging to prevent starvation with preemptive priority scheduling. Next, we'll talk about the round robin scheduling algorithm. Round robin scheduling is similar to the first come first serve scheduling which we talked about earlier. However, Preemption is added here in FCFS to enable the system to switch between processes. In this scheduling, every process gets to run on the CPU for a fixed amount of time called the time quantum. This time quantum is usually 10 to 100 milliseconds. So the way this works is the ready queue would be organized as first in first out queue, just as we do for the FCFS scheduling. The CPU scheduler will go around the ready queue, allocating the CPU to each process in this first in first out order for up to one time quantum. Let's assume that the time quantum is 100 milliseconds. Now let's say we have a process P1 which requires let's say only 78 milliseconds to execute on the CPU. So when this P1 is assigned the CPU for one time quantum, because P1 requires less time than the quantum length, it will finish within one time quantum and relinquish the CPU. So now the CPU scheduler will be invoked and it will move on to the next process in the ready queue. That is one possibility. Another possibility is, let's say process P1 instead of 78 milliseconds, let's say it required 780 milliseconds. So note that this is much longer than the time quantum length, which is only 100 milliseconds. So in this case, when the time the CPU burst of the process is much longer or longer than the allocated time quantum, there would be a timer interrupt at the end of the time quantum. So at the end of 100 milliseconds, the timer will go off and this will cause an interrupt to the operating system. So this interrupt will cause a context switch, and the process which was executing on the CPU, so basically let's say this P1 was executing, this P1 would be suspended and it would be put back at the end of the ready queue, and the CPU scheduler will then select the next process in the ready queue for scheduling on the CPU. Let's quickly think about the fairness property and also maybe the wait times that the processes will see with the round robin scheduling. Let's assume that this is our ready queue over here. It has n processes, P1, P2 all the way to Pn. Let's further assume that the time quantum in the round robin scheduling is exactly q time units. So in the round robin scheduling, every process here in the ready queue will get exactly 1 by n of the CPU time in chunks of at most q time units. Also, even if the process is, let's say, here at the end of the ready queue, each time quantum has a length of q time units, the process will have to wait at most for n-1 into q time units before it's done. So this n-1 are the other processes ahead of this last process in the queue. So let's take this example to better understand how round robin scheduling works. Let's assume we have these four processes P1, P2, P3 and P4 in our system, and their CPU bursts are as shown over here. Let's further assume that we are using this round robin scheduling where the length of the time quantum is 20 milliseconds. Let's say that for simplicity, let's assume that all of these four processes entered the system at time t equal to 0. So this is when they arrived. However, they were admitted in the order indicated, right? So P1 was admitted first, followed by P2, followed by P3, followed by P4, as mentioned here. So given this information, let's now figure out the schedule for this round robin scheduler. So let's assume that this is time t equal to 0 and time is increasing towards the right. So let's assume this is our ready queue. These are the four processes P1, P2, P3 and P4 in the first in first out order. So recall from our discussion in the previous slide, essentially the round robin algorithm will treat this ready queue as a circular queue. So it will first schedule this process P1 in the first time quantum, then P2 will be scheduled in the second time quantum, P3 in the third time quantum, P4 in the fourth time quantum. Now if P1 has not finished, we'll come back and in the fifth time quantum again we'll allow P1 to execute, followed by P2, followed by P3, followed by P4 in time quantum 8 and so forth. This process continues until all the four processes P1, P2 and P3 and P4 complete and terminate. So with that background, let's draw out this Gantt chart over here, right? So in the first time quantum, we'll allow process P1 to execute. So P1 would be allowed to execute for 20 milliseconds. So P1 will start at time 0 and it will finish here at time 20 milliseconds. Note that the CPU burst for P1 is 53. So P1 cannot finish in just 20 milliseconds. So at the end of the first time quantum, P1 will have executed for 20 milliseconds. So its remaining CPU burst would be 53 minus 20, which is 33 milliseconds. Next we'll schedule P2. So P2 will go next. It will again be allowed for one time quantum, which is 20 milliseconds, but note that P2 has a burst time of just 17. Okay, so it doesn't require the entire time quantum duration. It will just finish after 20 plus 17, which is basically at 37 milliseconds. So at this time P2 has completely executed and its remaining CPU burst time is 0. So P2 will exit the system. Next we'll schedule P3 for execution. Again this will be allowed to run for one time quantum, which is 20 milliseconds. So P3 requires 68 milliseconds, which is more than 20. So at the end of the third time quantum, P3 will have 68 minus 20, 48 milliseconds remaining. After this, so basically P3 will be preempted at time 37 plus 20, which is 57. After this, process P4 will be scheduled for the next 20 milliseconds. So P4 will be preempted at 57 plus 20 times 77, and at the end of this first time quantum, P4 will have 24 minus 20, only 4 milliseconds remaining. Now we have gone through the ready queue one full iteration, so we'll come back and we'll again check whether we'll again start from basically P1. So P1 still has more time to go. It has 33 more milliseconds, so we'll again schedule P1 for 20 more milliseconds, which is one time quantum. So P1 will now be preempted at 77 plus 20, which is 97 milliseconds. After this second time quantum for P1, it will have 33 minus 20, 13 milliseconds remaining. After P1, well, P2 has already terminated, so no need to schedule P2. We can move on directly to P3. So P3 will be scheduled again for 20 milliseconds. So this will run from 97 to 117. At the end of this second time quantum for P3, it will have 48 minus 20, 28 milliseconds remaining. Next we come to P4. Now P4 will also be allotted one time quantum, but P4 only requires 4 milliseconds. So P4 will exit the system at 117 plus 4, basically 121 milliseconds. And at the end of this, P4 has 0 milliseconds remaining, so P4 will also terminate and exit the system. So we now only just have P1 and P3 remaining in the system. So we'll come back in the circular fashion. We'll again schedule process P1. So P1 will be allotted one time quantum, but it just has 13 milliseconds remaining. So it will run from 121 to another 13 milliseconds, which is basically up to 134 milliseconds, 121 plus 13. So P1 completes at this time. After this round, P1 has 0 milliseconds remaining. Only P3 is in the system. So P3 will be scheduled next in the on the CPU. It will run for next 20 milliseconds, which is one time quantum. So it will be again suspended at time 134 plus 20, which is 154. At the end of this iteration, it has 28 minus 20, just 8 milliseconds to go. Now there is only one process remaining in the system, which is P3. So we'll again schedule P3 in the next round, and this time it will only finish. It has just 8 milliseconds remaining, so it won't take the entire time quantum. It will finish at 154 plus 8, which basically 162. So now P3 has also finished execution. The primary advantage of round robin scheduling is that starvation is not possible here. So note that we arrange the processes in first out order, and we go around this ready queue in a round robin fashion, allocating every process one time quantum to execute on the CPU, and therefore every process is guaranteed to get a chance to execute on the CPU. There is no indefinite waiting for any process. Another advantage of round robin scheduling is that the average response time of round robin scheduling is better as compared to the shortest remaining time first scheduling algorithm, which is a good thing for interactive systems. It also has its disadvantages. Even though the response time for round robin scheduling is better, the average waiting time for round robin scheduling are usually long. It is definitely longer than as compared to the shortest remaining time first algorithm. Another disadvantage of the round robin scheduling is that in general it has increased number of context switches. Note that every process is allowed to run on the CPU for one time quantum, and if it does not finish within the one time quantum, the process is preempted and put back at the end of the ready queue. This preemption of processes at the end of the time quantum overall increases the number of context switches in the system. You would recall from our previous discussion that context switch time is pure overhead. This is not useful work that a user process is doing, and therefore in general we would like to minimize the overall context switch overhead in the system. So how to do that? Well, if the time quantum length is long, right? If the length of the time quantum is large, most of the processes would be able to finish within one time quantum. So theoretically, if you set the length of the time quantum equal to infinity, right? So if you allow infinite time, essentially the round robin algorithm will degenerate into an Fcfs algorithm, because recall, in this round robin algorithm we arrange the ready queue as a first in first out queue, and we go around the processes as allocating them one time quantum in this first in first out order. And therefore if we allow an infinite time or unlimited time to every process within a time quantum, the round robin algorithm is essentially the same as the Fcfs or the first in first out algorithm. On the other hand, if we choose a very small time quantum, maybe 1 millisecond or shorter, there would be a lot of context switches, because most of the processes will not be able to finish within one time quantum, which means the context switch overhead would be too high. Based on this discussion, you would note that it is important to carefully choose the size of time quantum in the round robin scheduling algorithm. In practice, most modern systems have a time quantum ranging from 10 milliseconds to 100 milliseconds. And usually the time required for a context switch is typically less than 10 microseconds. So, well, 10 microseconds is very small as compared to 10 to 100 milliseconds. In general, the overall context switch overhead is fairly small if most processes are able to finish their next CPU burst within one single time quantum. A good rule of thumb is that 80% of the CPU burst should be shorter than the length of the time quantum. So this is how the time quantum length is determined in round robin scheduling.